Hello, this is the UI and code overview for Group 11, Proposal 7, to develop a hardware-in-the-loop simulation and a machine learning algorithm. So we are working with a project developed by AgJunction that they wrote in C. They have a system that contains multiple components and a mobile application. We are developing a simulation for that system. So this hardware in the loop simulation that we are developing will feed data into that system. AgJunction has a program that they have written in C, and we will be developing a program in C++ to feed data into that C program. Next, we are also going to be developing a machine learning algorithm that will use data that is produced by the hardware in the loop simulation. So as the hardware in the loop simulation feeds data into that system, the system will be writing that data to log files on a Linux system. The machine learning algorithm will pull those log files, scan them, and identify anomalous behavior based on parameters that AgJunction and we identify. Lastly, we will be developing a system to log those files. So when the simulation feeds data to the system, the results that are produced will be logged into a Linux system. So as you can see in the diagram, in the boxes that are highlighted in red, you could see what we will be doing as far as code and user interface. And some C and C++ tasks that we've identified is first, we need to develop a basic read-write system for saving Linux log files. So we will be writing that in C++ so that these log files can be written to the Linux system, as well as we could scan through all of those log files and pull data from them. Second will be our machine learning algorithm. This is the algorithm that is pulling data from those log files and scanning them for anomalies, and then those anomalies will be identified and sent to the user. Next is developing a program in C++ that could feed simulation data to the system. So AgJunction has provided us with a C program. We will be developing our program in C++ to feed data to their system. And next, moving over to the activity diagram. This is just a basic overview of how we see the system working. So it's the simulation starts, and we are then feeding data with using our hardware in loop simulation written in C++ to AgJunction's program. Results are produced and then logged into a Linux system, and the machine learning algorithm will pull the anomalies from those log files. So just a quick overview of the activity diagram is here. It gives the basics of how this program is going to run and how the C++ code that we will be adding to AgJunction's existing C program. Here is our Google Drive. It contains all of the products that we have created during this course, as well as products that AgJunction has provided us. We have our design artifacts, which will contain this video as well as future products. We've also posted our individual design review videos that we submitted earlier. We have diagrams that AgJunction provided us. Right here is the schematics of their system, and we will be using this to help with our hardware in the loop simulation. Going back, we have our live discussion notes and meeting minutes. We have the documents that we keep track of for the meetings that we have. Due to the proprietary nature of the code, AgJunction required us to sign a non-disclosure agreement. We have produced those and submitted them so we could access the code. We have all of our planning and project review documents. These documents are for our actual project plan, our presentation, and other documentation that we prepared with regards to planning for this system. Next, we have our sprint and retro planning documents. These contain all of our sprint planning documents. Lastly, we'll take a look at the code here that AgJunction provided to us. It contains different C files as well as header files. you have the IMU, the main file, and this is where our hardware in the loop simulation will be feeding data to the C code. So then it will then write to the Linux log files. This is the Jira board that we share along with Ag Junction. It has tasks that we have to do as a team as well as tasks for Ag Junction. This is one of the issues that we are looking at for the code. So for this, it is to review the RIMU code. The assignee and reporter are both posted here, as well as the latest updates to what has been done with this task. So for reviewing the RIMU code, we have the latest updates about what code needs to be produced moving forward. And this is an overview of the sprint. It has the tasks listed below and who they are assigned to. This is our sprint backlog. It has the issues and tasks that each team member will be assigned to. Looking down, what we are working on right now is we are still getting all of our access with the NDAs and SSH keys, reviewing the code and deciding what needs to be produced, what do we have to develop with the code to be implemented with Ag Junction's current system. So moving down, we are going to be using Weebots, so we have to familiarize ourselves with that interface, as well as several other issues involving Weebots. Continuing to move down, we look at some of the machine learning algorithm tasks, as well as further issues with Weebots and reviewing the RIMU code.
All right, so here we are in our Weebot simulation software. This is the software we'll be using to create our simulated farm environment for our tractor to drive on for this project. Weebots comes with a bunch of different sample worlds that you can kind of play around with. So for this simulation of the farmland that I have here, I chose a sample world called Boomer, and I just built on top of that. So when I loaded the original sample world, I got just a square piece of land and I got this tractor. The land was flat and the land had a texture of sand. And I played around with this a little bit to learn how to get different lands and different textures. So this brown area here is actually supposed to resemble dirt. This green square here is supposed to resemble a cornfield. And when I turn this view to the side, you can see that the cornfield is actually uneven terrain as opposed to the flat land that originally came with the sample world. And to get all these different components to be more unique from the sample world, I worked over here in this pane on the left. It's called, what Weebots calls it, this scene tree. And this is where you can add new components or modify existing components. So you can see here, I added the bungalow style house. I have an uneven terrain, which is the cornfield. And when I open this up, you can change the texture. So I have it set as cornfield. You can change the position of where the field is, so you can kind of move it around on the simulation. There's a bunch of different things you can do with this, and we're still playing around with it to know exactly the power Weebots has to create the simulation. But I think so far we have a pretty good footing. We have a pretty good understanding of how to get this to work. So when this simulation gets saved, it's actually saved as a WBT file, which is the world file. And that's the file that others can use to upload to their own Weebots software. So when I save this file, I can share this file with my teammates and they can upload it into their Weebots application and they should get this exact same world. This black box up here in the corner is a camera, and that actually came with the tractor. It's a camera that is on front of the in the front of the tractor. So when I start the simulation here in a second, you can actually see what the tractor is seeing up here in this black box. So I'll go ahead and get the simulation started here. And the tractor starts moving along the field, and we can steer the tractor and accelerate it or decelerate it. And the direction and the speed is all controlled by the arrow keys right now. However, it is our intention to program the tractor to actually um, have a program to find its way through the field. Our plan is to have the tractor run the perimeter of the property, and once it gets through bordering the property, then it'll go up and down to create those lines that you see in farms today. So this is our simulation that we have so far. There's still more work to be done, but as I said, I think we have a pretty good understanding, and I think we should be able to get a really cool simulation running soon.